mean, at UCLA, we're obviously deeply concerned about the environment, and probably the way we have the most impact is through the scholarship that goes on. And you're going to hear some dazzling work by Professor Sant, who's really one of our leaders in this area, running an institute on carbon management. So that's probably our greatest contribution. But we're also educating students who can be good citizens and good stewards of this planet, but also well informed of these issues and hopefully can help solve some of the problems. I will mention, we're now neighbors here. Many of you have heard we bought property here. We bought a campus actually in Metro Palos Verdes and housing in San Pedro. So we're looking forward to lots of opportunities here at the port. So I think we can have deeper engagement with the port, deeper engagement with everyone who's here trying to really solve these very vexing problems. So thank you again. Thanks to all our partners. We look forward to a really interesting group of speakers. Thank you.
So with that, I'd like to invite our first panel on carbon management up here with Dr. Sant, who Chancellor Bach just mentioned, Hillary Patricio and Naoki Hara. So if you guys want to come up and join me here on stage. In the meantime, I'd like to invite everyone in the back of the room. I know we have a lot of newcomers. Some of the infamous LA traffic kind of slowed down the start of the event tonight. But come on out, we have plenty of seats up here. We'd love for you to join. We're going to have a brief conversation with two panels here, and then I promise we'll let everyone get to the food and the booze afterward. But by all means, please take a seat. Yes, absolutely. All right. Dr. Sant. So, we have three remarkable speakers to talk tonight about carbon management, and these folks are much smarter than I am and much more well-versed in the topic than I am. So I think a great way just to kind of get the topic introduced rather than having me pretend like I'm an expert in this field is really just to hand the panel off. We'll start out with Dr. Sant. We have a few slides. Actually, Dr. Sant's just going to kind of free flow here, and we have a couple of slides. So as you guys progress through your slides, if you'll just tell our department this next slide. We have really kind of a scientific rock star in the house tonight with Dr. Sant. We're all really excited, not only to hear about your work at UCLA, but the work that you're doing here at AltaSea. So without further ado, Dr. Sant.
Thanks very much, Brian. So I'm going to be on my best behavior because my boss is in the room. But with that said, thanks everyone for being here. My name is DriveH2 Sant. I'm a professor of engineering at UCLA. I've been at UCLA for over a decade. It's been a wonderful time. So I run the Institute for Carbon Management, and we're a translational institute. What that means is, unlike a typical university institute, we don't do purely discovery research, we do translation. So what that means is, we work on interesting things and then turn them into real-life processes and systems. So there's two areas that we work in, and it's going to touch a little bit on the stuff that Terry said, a little bit of stuff that Brian's been talking about, lots of things that are in the news. But we work in a principal area around carbon management, which is thinking about avoidance, removal, and the utilization of carbon dioxide emissions in carbon dioxide from the atmosphere. And the way that we do it is using the oceans. Why? There's carbon dioxide in the atmosphere, there's proportionally an amount of carbon dioxide in the oceans. Water contains about 150 times more carbon dioxide than air, which means if you want to remove carbon dioxide from the atmosphere, one of the most effective ways to do it is in fact by removing it from the oceans. Because if you take a sponge, fill up a sponge with water, squeeze it out, it's ready to absorb some more water again. Sort of the same analogy with the oceans. And so the system that we're building that's going to hang out outside on a barge is actually going to do exactly that. It's going to show for the first time ever how to do this at a meaningful scale. I was actually just telling Rob Fisher, who's on the back somewhere, about the story a few minutes ago. But exactly about 2 years ago, this was an experiment about that big at a lab at UCLA. Now it's going to live on the top of a barge. So it's been an interesting adventure. With that said, I'll hand it off to Hillary. And thanks again for being here.
Hello, thank you all. My name is Hillary Patricio, and I am a commercial development manager at SoCalGas, and my focus is on carbon capture, utilization, and sequestration. And I was very excited to be invited to this event because I'm a Bruin, so proof positive that Bruins go on to do great things, including focusing on carbon management. And do I have slides? Can you folks see slides? one of the things that we were talking about, thank you, that my kids were noting is they learned that recycling has 3 R's: reduce, reuse, recycle. And I think this is a perfect analogy for carbon management. So moving from left to right, we're going to start with capture, we're going to move to transport and storage, and then utilization. And that actually really follows well: reduce, reuse, recycle. So as my son was telling me, the most important thing to do is reduce. So I think we're all aware we need to reduce our emissions. We have the hydrogen panel coming up later, so it'll be great to focus on new clean fuels. So definitely reducing our emissions through clean fuels is important. But we also need to reduce the amount of CO2 that we're emitting. So you can see the 2 focuses up here. We've got point source. So point source capture, far more effective. There's higher volumes of CO2 coming from ethanol, from cement plants. So that's one big focus, is point source capture. But like some of the other folks are talking about, you can also capture from the ocean and the air. So there's different mechanisms to capture. So that's where reduce comes into play. So now that you've captured the CO2, the next step, of course, is to transport it. And you transport it focusing on either 2 options. The permanent storage, so that's injecting it thousands of feet underground to just stay there, or you can use it for utilization. So when you think about permanent storage, that's where I see the use coming in. So I did used to be a petroleum geologist up in Bakersfield. There's a lot of depleted oil fields in California. California, I don't know if everyone knows, has been a huge oil producer for 100 years, which means now there's an opportunity to reuse these depleted oil fields to potentially inject CO2 in them permanently. And then again, moving to the last part, so recycling. Turns out, yes, as my son was telling me, recycling is kind of the least impactful. It's far more important to reuse and reuse. But recycling is the cool part. That's where the innovation comes in. So there's lots of things being done with carbon cement, making clothing, making sunglasses. So that's what we can get excited about. Next slide, please. So some other good news, there's a lot of federal funding to advance all these projects. So the Department of Energy has opened up, over the next 5 years, $12 billion in funding for carbon management projects. And the way that the projects are being funded is very much tied to what aspect of that value chain are you focused on. So there's a big focus on the capture. For example, there's an application open right now for direct air capture hubs. So focusing on how can you have a massive, large-scale direct air capture system, recognizing direct air capture is less efficient, but at scale it can be very impactful. There's also funding focused on transport. So this is where SoCalGas is interested in playing a role. And we've been operating for 150 years. We're a pipeline company. So we're really focused on how can we leverage this knowledge, our operations department, our risk management department, our gas control department, all the different things we do well into a future where we own and operate CO2 pipelines. So we provide that transport service to take the CO2, again, to its permanent home, either for storage or utilization. But again, a lot of federal funding for this, so it's a really exciting time to be in carbon management, and a lot of different opportunities to apply for. Last slide, please. So just to wrap it up, here's the vision for SoCalGas. So I talked about being a petroleum geologist in Bakersfield. That's where a lot of the potential storage is, both in depleted oil and gas fields, but also potentially in saline aquifers. So really our vision is how can we start in Kern County, work with partners there. But we're also recognizing that there's lots of emission sources that are across Southern California, particularly a lot in the area we are now. So looking at maybe future phases where there could be capture in this region and brought up to permanent storage in the Kern County region. So this is our vision. We're very much at the early stages, very much in the study and feasibility stage. We're looking to see how we can work with partners, how can we bring this DOE funding to California to start making an impact. So thank you, and happy to answer more questions.
I will be lobbing a lot of questions at you. So, all right. So, to close out the introductions, I'm going to invite Naomi Hara to come up here and talk a little bit about your work at JFE, and then we'll jump into some of the questions. So, thank you very much.
My name is Naoki Han, and I'm the president of JFE Engineering Firm, located downtown Long Beach, just 10-minute drive away from here. I want to say thank you so much for inviting me today, and I'm honored to be here to talk about how we are working on decarbonization. Next slide, please. J3 Group started as steel manufacturing, shipbuilding, and comprehensive engineering firm in 1912. So it's been around for more than a century, and we have been a solid steel supplier as one of the leading steel conglomerates in Japan. Like a port, we closely deal with the demand for economic growth to fulfill our social responsibility. We supply steel to automakers, shipbuilders, bridge makers, heavy machinery, and so on. But simultaneously, we must meet the decarbonization demand to fulfill our social responsibility again. From such point of view, I'm happy to share my ideas and experiences in the discussion today. Next slide, please. First, we have come to a decision to invest over $400 million US in manufacturing plant for offshore wind turbines, monopiles, as well as transition pieces. This is one good example of J3 technology will be used for generating this kind of renewable energy industry. Next slide, please. This is an example that the demonstration devices that utilize CO2 from exhausting gas coming out from waste to energy plant. We are trying to make a methane or methanol from CO2 capture system. And this gasifying melting furnace systems technologies came from our steel blast furnace technology. Next slide, please. And the last slide, this is a fully automated bicycle storage system. This is a unique technology that has been used for many places in Japan. For instance, metro stations, residential areas, office buildings, shopping malls, and much more. Not only they have installed for purpose of a environmentally friendly products, but also they have installed for purpose of cyclist convenience. You don't need to hassle finding your parking spot. No one will be able to touch your nice, fancy, beautiful bicycle. And the prevention of any chances of theft. So all those efforts is associated with decarbonization using J3 technologies. Thank you.
From private industry in terms of applications and how we're seeing this in the field. And if I could ask everyone to please quiet down in the back, we'll push through the panel discussion here. I've got a few quick questions for our panelists. I don't really want to put anybody on the spot, but rumor has it that a byproduct of Dr. Song's technology is hydrogen production, and as you may have noticed, there are a lot of hydrogen fans in the room here. So I'm hoping you might be able to walk us through a little bit of kind of the crossroads where carbon capture and hydrogen technologies meet.
Yeah, so great question, Ryan. So when we started to think about carbon management, one of the fundamental premises that we rely on is that you need a way to cross-subsidize the cost of carbon management. Carbon management in and of itself obviously implies a cost. We were interested in trying to understand if there's a synergy that you can realize where clean energy production and carbon management can coincide. And it sort of seemed very serendipitous, but we decided to rely on this process of what's known as electrolysis, right? So one of the ways that you can produce hydrogen is you effectively run a current through water, right? As you run a current through water, you can essentially start to split water apart. Water is composed of hydrogen and oxygen, so you can produce hydrogen gas. You can also produce oxygen gas. And electrolysis is something we've been doing for a long time. Depending on how you choose to look at it, it's been a couple of 100 years now. We saw an interesting opportunity by which we could actually exploit electrolysis to do both hydrogen production and carbon removal. And we realized we could actually do it with the oceans, right? So when you have water, you can essentially run electricity through water. You can start to reorganize the components of water, the elements that make up water, in a way that you produce hydrogen and oxygen, but you also produce acid and base. Now the acid and base production part is important. So if you think about carbon dioxide, this is me being a college professor, it's an acid, right? Carbon dioxide being an acid is quite important because the way that you actually consume an acid is with a base, right? Now, the reason that this starts to make a lot of sense is if you're producing a base, which is something you can do with electrolysis, and you have carbon dioxide in water or in the atmosphere, which is an acid, you can consume carbon dioxide with an electrolysis process. The second thing that you can do is because electrolysis allows the production of hydrogen and oxygen, you also end up producing hydrogen, which is a clean fuel, and oxygen, which we breathe, but in addition to sort of breathing in oxygen, oxygen is really attractive because it makes every combustion process around you far more efficient. And so we saw an interesting opportunity where we could sort of couple a lot of things together within a single process. And when we first started to think about it, we said, this sounds wonderful, but it's probably going to be really hard. It's one of these things, right? The more you work on something, the more you know about it, the simpler it seems. And until you've not done it, it seems like impossible to do. The longer we worked on this, we realized that there was actually a real opportunity to do this. We started out, like I said, with little pen scale experiments, so to speak. And at every point that we thought it would fail, it did not, right? And then you get really suspicious. It's like, why? So we continued down this train of path, and we realized that in fact you could actually build a chemical process doing this that does carbon removal, hydrogen production all at the same time. And so in fact this rig that's going to sit out on the barge outside there is going to do exactly that. It'll produce hydrogen and it'll achieve carbon removal. Now for everyone that's in the room, right, the eventual question is how much is it going to cost? Super important. And I was talking to Hillary about this for a few minutes before we decided to walk right along and come hang out here. But in effect, with the work that we're doing, we see a realistic, credible, short-term pathway to achieve atmospheric carbon dioxide removal at less than $100 a ton. That's a really important number for anyone that's not familiar with it. But importantly, we see the ability to produce hydrogen at about $1 a kilogram, right? And I think that's sort of the economics eventually drives this because you've got to rest on the economics for market pickup. And so that's a little bit of what we're up to.
Oh wow, that leads to so many more questions, and I have some questions for the other panelists. But since you mentioned the $100 a ton threshold, right? Can you give us an idea of what current prices are? And I guess maybe the audience isn't quite aware of how much CO2 we're producing for industrial purposes and actually selling on an open market. So can you give us an idea of how much CO2 is selling for in terms of like food and beverage and some of the other big applications? And what's the gap between that CO2 versus what we're trying to capture and put into the market?
So this is sort of an interesting point. It's not perfectly correlated, but a lot of the carbon dioxide that we get as an example from industrial processes, right? From what are known as air separation units. So you actually want some other gas, right? So you're essentially going to do what's known as a distillation of air. You're going to break down air into its primary components. So that's one of the ways that you get carbon dioxide. The other way that you get it is from ethanol plants, right? So you produce bioethanol as an example from agricultural feedstock, right? So you think about blended fuel as an example. That's another place that we get CO2. So most CO2 that's sold in the merchant market, in the commercial market, typically comes from these sources. Depending on where you are, the CO2 is actually not that expensive. You can actually get the CO2 for free. If it sells, it's no more than $100 a ton. The challenge around moving CO2 is we don't have a tanker supply fleet anywhere in the US to be able to move carbon dioxide effectively. So that's one of the things that complicates it. We have pipelines. Pipelines basically in 2 states, Oklahoma and Texas. Most of them owned by effectively one company, Kinder Morgan, that you use to move carbon dioxide around. Where this gets a whole lot more complex is when you think about the balance around how much carbon dioxide we actually emit into the atmosphere. And I think that scale is important to keep in mind. We put about 40 billion tons of carbon dioxide into the atmosphere. And if you think about how much this is, we produce a lot of concrete. I train to be a cement chemist. We produce about 25 billion tons of concrete. So actually we put more carbon dioxide into the atmosphere than all the concrete that we produce, right? So when you think about the scale of this problem, super large. And that's why economics start to become important. It's all about scale.
All right, so if I understand you correctly, part of the obstacle in this space is really the cost of distribution or the means of distribution. Luckily, we have an expert on the panel that knows a little bit about CO2 distribution. So could you talk to us a little bit about kind of what economies of scale we need to hit in order to bring that cost of distribution lower, what technologies you might be particularly excited about, and then I'll pause there and I have another related question for you.
So yeah, we are looking at cost of pipelines and how they compare to typical natural gas pipelines, but the scale is a big thing that we're looking at. And I'd say the best thing to look at in terms of scale is what a lot of the Department of Energy projects are focused on. So when you're looking at projects that they want to fund that capture from the point sources, they're looking at like 50 million tons over 30 years. When you look at what they're trying to fund in terms of direct air capture, then they're looking at starting out maybe 50,000 tons a year, but scaling up to 1 million tons a year. So when we're thinking about building a pipeline, really the focus is on, we want to build it for that eventual 1 million tons a year, not the 50,000 to start. And I think the DOE agrees because there's some funding opportunities out there on, if you're already intending to build a pipeline, putting the investment in the engineering, the design and the cost, why not build it bigger now so that you can accommodate those future sources to really get to the scale that will make an impact.
All right, great. So I'd just like to tap on an additional question there. What is the role of the policy community in helping close that gap? And it seems like your role with the utility, there's obviously, you're